Hey everybody, we are back now for kind of the second half of precipitation reactions, but also generally this idea of something called a net-ionic equation. One of the things that the College Board will ask you to do is they'll ask you to take a chemical reaction and write the net-ionic equation for it compared to what we are used to writing, which is called the molecular equation. So we're going to go over the difference between those things, and then we're going to talk about particle diagrams and how you draw a picture of a chemical reaction, okay? So when we talk about a net-ionic equation, what a net-ionic equation is it's a chemical equation that shows only the elements, compounds, and ions that are directly involved in a chemical reaction and are actually going through the change process. And you might say to yourself, but when I look at a chemical reaction, all of it's changing. And while technically the rearrangement is changing from start to finish in a chemical reaction, what can happen sometimes is some things that may appear to change don't actually change in the process. And so the net-ionic equation leaves out the unchanged things. The things that don't change in your chemical reaction are called spectator ions. And they are called spectator ions because they just sit around and watch your chemical reaction. So there are a couple different scenarios that I want to show you guys with these net-ionic equations and what you can kind of see with them. And then we're going to talk about how you draw them. And honestly, the hardest part is trying to kind of visualize what they look like. But if you can visualize what they look like, I think it helps us write the net-ionic equation. So we're going to look at a series of three equations that zinc is undergoing, and then, or a zinc-related compound, and then we're going to talk about them. Okay, so here is the first one. It is solid zinc reacting with aqueous hydrochloric acid, and it's turning into aqueous zinc chloride and hydrogen gas. So when you look at these equations, I always try to make a mental picture in my head of what is happening. And so remember, phases, solid phase, our particles are clustered together. Liquid phase, it's pure chemical, but it's able to kind of move around and there's empty space, more space between the particles. And if I have a gas, my gas is kind of particles, but there's tons of room and lots of empty space between them. And if I have an aqueous solution, my ions break apart into their individual ions. And then the empty space that I draw in the picture is water. So I'll show you what I mean by that. This is my drawing of this reaction. So if you see here, I've kind of got this little cluster of zinc particles here that are in the solid phase. Now, sometimes they might just draw that as an actual like little pile of zinc instead of individual atoms, but I've got the solid represented by the fact that it's all tight together. My hydrochloric acid here, that is aqueous. So because it's aqueous, it means it's going to break into its individual ions. Most acids do this, and there is a discussion about strong acids versus weak acids that we will get into when we actually get into acids and bases. But for now, think about just your compounds that are kind of ionic like this. They are going to break apart. So in the case of these acids here, I have H plus ions and I have chloride ions floating around. Now you'll notice in these pictures, the subscripts in my H and Cl are 1 and 1. So when I draw my picture, I make sure that I have a 1-to-1 ratio here. So for every 1 H plus, I get a Cl minus. Okay. So really when these two things mix together, I have hydrogen ions getting together with the zinc and potentially the chloride ions getting together with the zinc. Okay. What they turn into is zinc chloride aqueous. So what I now have is an ionic solution that's actually zinc 2+ ions and chloride ions. Now you say to yourself, how did you know that? If you look at the zinc, we know that chloride has a -1 for its oxidation number, and it takes 2 of them to cancel out 1 zinc. So this zinc's oxidation number must be a +2. Okay. Here is my hydrogen gas kind of fizzing out probably the container, and then I'm left with these ions here. Now in this case, I am not going to be super fussy to start off with relative quantities of this because we aren't talking about stoichiometry yet, but in theory at some point we'll talk about like which should we have more of, which should we have less of, but right now not that big of a deal. Now if you look here, things are changing. The zinc is going from a solid zinc to a zinc ion. That's a change. The hydrogen is going from an ion into a gas form, but our chloride here, the Cl minus, doesn't change at all. And so that is what we call a spectator ion. Now, if I wanted to torture you, which I don't want to, I could make you write something called the ionic equation or the complete ionic equation. This equation that we are used to at the top here is called the molecular equation. What the complete ionic or ionic equation does is it shows every single participant in the reaction. So if you look here, the ionic equation is zinc solid plus 2 H's with a plus charge plus 2 Cl minuses, and they turn into Zn2 plus and 2 Cl minuses and H2. Now, the coefficient play a role in the ionic equation. So it's 2 H pluses and 2 Cl minuses, and this here, this little subscript of 2 also plays a role. So anytime you see more than one of something, that kind of becomes its coefficient in the overall ionic equation. What the net ionic equation does is it chops out spectator ions. So in both of these equations, you can kind of see on on both sides of the equation, you can see that the Cl minus stays the same in its charge and in its phase. And so that means it's a spectator ion. And I can cross those out. And now my net ionic equation is just the stuff that's changing. So my net ionic equation is Zn solid plus H pluses, and there's 2 of them, and that turns into Zn2 plus and H2 gas. So what we do is we leave those spectators out and we don't really care about them, okay? I would say it is important to be able to visualize these, and then if you can visualize what is not changing, you don't have to write the complete ionic equation. So we're going to do another one, and hopefully you can get this one figured out. So if you look at this one, it's ZNS plus CuNO3 2 turning into ZnNO3 2 aqueous and copper solid. So what I want you to mentally think about is what this is going to look like before we mix the things together and after we mix the things together. So if you need to pause the video, take a think, and then we'll come back and then take a look at what I think the picture looks like, okay? Okay, in my head, when I see this, I have a little pile of zinc again, and then I have a beaker, and inside my beaker, because copper nitrate is an ionic compound, I have copper 2 plus ions floating around in there and nitrate ions. And there are 2 nitrate ions for every copper because I have 2 for my subscript for the nitrate, okay? So that's my before. Afterwards, the copper solid must be sitting in, like I got to mix these things together, right? So in my new container, the copper is sitting as a solid in the bottom. I got my little copper atom sitting solid. And then because the zinc nitrate is aqueous, I have zinc 2 plus ions now and nitrate ions. And if you look in our picture here, nitrates remain nitrates, but the zinc goes from a solid to an ion and the copper goes from an ion to a solid. So when we think about our net ionic equation, we are going to leave out our spectator, the nitrate. And honestly, when we talk about our spectator ions, a lot of them tend to be like the sodiums, potassiums, nitrates that are in those aqueous compounds because we know that they're going to be soluble all the time. So coming up here, you'll see the complete ionic equation, and then you'll see the net ionic equation. I, again, don't think you have to write the ionic equation if you can visually figure out what's going on for the net ionic equation. So in this case, the zinc and the copper 2 plus are reacting together, and then the zinc 2 plus ion shows up, and so does copper solid. So in general, we have those things changing. The nitrate essentially is just a vehicle to drop the copper ion off, and then it can do its reaction. Okay? All right, last one. I feel like you can do this. So let's see if you can. I want you to draw the picture for this and then see if you can figure out the net ionic equation. We're going to have zinc nitrate, ZnNO3 2, plus Na2CO3, both aqueous, turning into zinc carbonate, which is solid, and 2NaNO3. So try to get, in this case, the picture, get your net ionic equation, and we'll come on back and take a look. All right, time to check your picture. So my beakers to begin with are going to be full of ions because I have aqueous solutions. So I've got zinc 2 plus ions, and I have nitrate ions floating around in a 2-to-1 ratio, 2 nitrates to 1 zinc. That's because of the subscript. Same thing with the sodium carbonate. It's 2 sodiums to 1 carbonate. When I mix them together, I produce zinc carbonate solid. Now, I did not feel like drawing little molecules down here. So all I did in this case is I drew a little like pile of solid down here. And then my NaNO3 is going to be aqueous, and it's a 1-to-1 ratio. Like I said, quantities aren't going to be super important here to begin with. We'll talk about them more with stoichiometry. Okay. Now, if you look at this, think about what isn't changing. I have zinc turning from an ion into a solid, and I have carbonate turning from an ion to being trapped in a solid. But the sodiums remain floating and the nitrates remain floating. So those are our spectator ions. So in this case, our net ionic equation is going to be way smaller than our actual complete ionic equation. The net ionic equation is going to be zinc 2 plus the carbonate, and it's turning into zinc carbonate solid. So if you look here, we've got the ion, we've got the carbonate, and we've got the solid. All the NAs are left out. All the nitrates are left out because they don't change. They are just, like I said, vehicles to deliver the actual participants. If you think about it, you're like at a soccer game. Parents drop you off when you're a little kid. They are the vehicle to deliver you, and then they sit and they watch you at the game while the little kids actually participate in the game. It's the same thing with these. Your spectator ions drop off your ions that are participating at the game, then they park it and they watch from the sidelines, and that's kind of how it works. Okay? On your homework, you're going to be asked to do this with your drawings. So after you get your reactions figured out for like your double replacement reactions and your solubility rules, then you're going to have to do these drawings. Okay, so if you have any questions, please make sure you get things cleared up. Otherwise, good luck.